I think they're off by one. I'll have to tell them. Should be lecture 16 because we had the midterm review. That shouldn't count as a lecture. Okay, so we can get started. Hello class, just wanted to make an announcement about the midterm, and I'll wait until the end of class to return the midterms because otherwise you guys will be gone. I remember what it was like to get a midterm. It was distracting. So let me give you the numbers though. So the mean on the midterm was 62, and that's for the whole class, and I broke it down into undergrad and grad. So the undergrad mean was 58 and the grad mean is 68. The maximums were actually pretty close. So the undergrad, so the total max was 83, undergrad was 81, and the min, again very similar. Overall min was 38, and the undergrads actually did better. It was a grad who earned the min. I think the results are pretty good. Looking at the exams, it looked like everybody knew more or less what they were doing. It was, again, just a badly designed exam. It was too long for the given time, so the fault is ours, not yours. I'll return the midterms at the end of class. If I forget, just remind me. Okay? All right, any questions before we get started? Comments? Good. All right, so last lecture we were talking about basically an IQ modulator. And the idea was that if we had two signals, I of t and q of t, which are signals as a function of time, and we multiply these by, let's say, sine and cosine, and we take the sum. We showed last lecture that this sum signal has an amplitude and a phase, which basically allows us to use this one dual mixer configuration to do amplitude modulation and phase modulation. So last lecture we showed that the amplitude of this signal coming out is I of t squared plus q of t squared square root, and the phase of the signal coming out is the inverse tangent of q over I. And there's a nice graphical interpretation for this. Graphical interpretation of this is that we can plot I and q separately. They're orthogonal from one another. So this is the I, this is the q. Again, this is the IQ plane. And if, for instance, if I want to modulate my signal in such a way as to keep the amplitude constant, that corresponds to a circle on this plane. So an example of that would be I could pick these 2 points and produce a digital modulation scheme where I either send I of, let's say, +1 or I of -1. And that corresponds to basically phase modulation. I'm changing the phase by 180 degrees. If I want to pack more information, I could actually pick 4 points and send these 4 points, basically encode my data. So this might be 0, 0, this might be 0, 1, this might be 1, 0, and this would be 1, 1. So in this way, I could basically group 2 bits together and then transmit one of these IQ signals, and that would represent the modulation. And I can use the simple modulator to do that. Now this is a constant envelope modulation, because of course this magnitude is A of t, and this is the phase phi of t. So the only thing that changes as we transmit different bits here is the phase. I could also do a more complicated modulation. For instance, I could send these 4 points on the IQ plane, and now you could see that the amplitude also changes. For instance, let me add some more points to try to pack more information. So you could see that now the envelope changes depending on what bit I send, and so does the phase. Okay? So this would be in general what's called a QAM modulation scheme. Now, I won't go into detail about modulation schemes and their performance, but let us just say that the performance of a modulation scheme, the probability that you make an error, is also very much related to signal-noise ratio. And we talked about this briefly before, because if I transmit bits on this, what we call this constellation, what we receive are not actually these points exactly, because there's going to be noise in the system. So what you would actually receive, you might, if you drew a bunch of bits that you received, they would generate, let's say, some scatter plots with clusters of points close to these original IQ points. And you can see that if you had to make a decision about if this bit were sent or if this bit were sent, you could do it as long as you were, you could be fairly confident that you're making the right decision, as long as, let's say, you're in this quadrant. If the noise is large enough that it moves you out of this quadrant, then you'll make an error when you're sending a 0, 0. In fact, you receive a 0, 1. So the space between these 2 points is very important. And remember, the space between these 2 points is related to this amplitude. And of course, that's related to the power of the signal. So if I wanted to reduce the probability of error, I would basically scale this. I would send A of t, which is bigger. So in other words, if this were the original constellation, I would do much better to send this constellation, right? Because now the probability of error is much smaller. And of course, the amount of spread, the RMS value of the spread here, is also related to, so this is the RMS spread, is related to the amount of noise in the channel. And so you can see that signal-noise ratio plays a big role in determining when you make an error. So, of course, the point of this lecture is not really to understand the digital modulation scheme. That's the topic of another course like 121. The point here is that I can take 2 mixers like this and basically design a modulator that can modulate either amplitude or phase. Okay? Any questions about that? Yes?
Can you elaborate on the frequency modulation on this diagram?
Sure. So basically, if I constantly change my phase, so if instead of sending discrete points, I send motion right along this circle, that corresponds to frequency modulation, right? So if I take d phi dt, right, so if I move constantly along this point, that corresponds to frequency 1, right? So it's the rate at which I change the phase, which is the frequency. If I move faster, that corresponds to a higher frequency. Okay, good question. Any other questions? Okay, so this IQ mixer also has a lot of other nice applications. Let me talk about the IQ mixer for image rejection. And this is something you'll need for this homework. So let me just draw the mixer, and then we'll talk about how it works. So again, let's say I have an LNA, and instead of going into a mixer, as we talked about last lecture, I go into one of these IQ mixers. So again, this is cosine omega t, this is sine omega t. And at the output of this mixer, I'm going to introduce a 90-degree delay. And we'll see why in a moment. And then I'm going to take these 2 signals and add them up and produce my IF. Okay? So if we compare this to what we talked about last lecture, we introduced a filter. We had an image rejection filter. So we called this the image reject filter. And this lecture, what I'm claiming is that basically, if this thing were to work perfectly, you could get rid of this image reject filter. You wouldn't need it. Because this is inherently an image reject mixer architecture. This one is called a Hartley mixer. Okay? So let's see how this works. And to do that, we're going to kind of build up, it up point by point. So first of all, let's take this 90 degrees delay block and see why we need that, and in fact, what does a 90-degree block do. So let's talk about the 90-degree phase delay block. Okay. If you imagine basically a sine wave, and if I delay that by 90 degrees, I know I get a cosine wave, right? If I just shift this backwards, so this is sine, this is cosine. So this corresponds to a shift of 90 degrees in the sinusoid produces a cosine. Okay? Now this is very obvious, right? But let's see what, if we look in the complex plane, what's going on. Okay? So in the complex plane, I can write sine of x as e to the jx minus e to the minus jx divided by 2j. And now let me introduce my phase shift of pi over 2, or 90 degrees. So that gives me e to the j pi over 2, e to the jx minus e to the minus j pi over 2, e to the minus jx divided by 2j. Well, in the complex plane, I know that a phase shift of pi over 2, e to the j pi over 2 is just plus j, and e to the minus pi over 2 is just minus j, right? So here I have plus j e to the jx minus minus e to the minus jx times j divided by 2j. And you can see the j's all cancel out, and indeed I get cosine of x just as expected. Okay. Now, why did I go through this exercise? The reason I went through this exercise is that if we look to see what happens to the individual exponential terms in this signal, if you observe that in going from here to here, what happened was in the phase delay, this term got multiplied by positive j, and this term got multiplied by negative j. Okay? So basically what we can say is a phase delay of 90 degrees basically is like multiplying by plus or minus j, depending on sign of frequency. Okay? And because I can basically decompose any arbitrary modulation into a sum of complex exponentials, right? That's a Fourier series representation. Then I could say that if I were to delay that signal, that corresponds to multiplying it by j or minus j, depending on if the frequencies are positive or negative. Okay? Questions? Okay. Well, let's also take a look at modulation a little bit more carefully. So let me go back and look at modulation. Yes?
What do you mean by, so are you saying that the negative jx is a negative frequency? How are you exactly, I guess, defining frequency, like as far as when you say the sign of the frequency?
Yeah, so if I think of this sine wave, right, this corresponds to basically 1 over 2j here and minus 1 over 2j. Right? And so what we see is that in delaying it, what happens at the end of the day, I end up with 1/2 and 1/2 here. Right? This is the cosine. So this term with the positive frequency, it looked like it just got multiplied by j. This term here got multiplied by minus j because its magnitude flipped, or its phase flipped. Okay. Any other questions? Okay. So modulation, in fact, if we look at frequency multiplication, so this is multiplication in time. By a sinusoid. That's what we defined as a perfect mixer operation. Let me take the Fourier transform of cosine, let's say, omega mt. This is our modulated waveform, times some arbitrary time domain waveform. This is our signal. Okay? So by definition, Fourier transform is f of t cosine omega t, this is the function, times e to the minus j omega t integrate over all time, right? This is the definition of Fourier transform. Well, if I write the cosine term as e to the j omega mt plus e to the minus j omega mt divided by 2, then I can basically group these terms here. So this turns into two integrals, f of t e to the j omega m minus omega t divided by 2 plus f of t e to the minus j omega plus omega m t divided by 2 dt, right? And then you recognize this first term as 1/2 the Fourier transform of f. This is as if I'm doing basically a new Fourier transform in this frequency shifted plane. So this is this term, and the second term, so this should actually be minus plus, and this term will just be omega m plus omega. Okay? And of course, if you guys remember your linear system theory, this is trivial. When you multiply by a complex exponential, it corresponds to a frequency shift, right? And that's what modulation is all about. Okay. Any questions about how we got this term? So now we see that when we take our arbitrary waveform here, f of t, and multiply it by cosine, we can think of it as being multiplied individually by two complex exponentials. And multiplying by basically e to the positive j omega mt produces this term. Let me draw a picture to make it more clear. Okay, so I start out with my arbitrary, let's say, waveform at some frequency omega rf. Let's say this is omega m, and this is the difference frequency. Let me put it over here. This is my IF frequency. IF is omega RF minus omega m. And because this is a real spectrum, I have to also consider the fact that it's an even function, and so if I transmit this, I also have to transmit this, right? So then I also have two frequency components and a minus IF frequency. Okay. Now, if I simply were to multiply by this term, which is e to the j omega mt, then according to this calculation, we can see that what will happen is I will get two terms. I will get, first of all, this term with a factor of 1/2, which corresponds to omega minus omega m. I will get this term, which is omega plus omega m. Okay? And that's actually the desired down conversion, but because there's this negative frequency, I also have to take into account that I get a term which appears here and somewhere out here, which I won't draw. Okay? So just multiplying by one of these complex exponentials actually nicely does the trick. It moves my spectrum down to baseband. Okay? And what's interesting is that there is no image problem, right? What if I had... this is a bad picture. Let me draw a slightly better picture. This is the RF. This is the LO. And now this is the image. So let me say I have a signal here, and let's say I have some noise signal here. So due to the multiplication by this, my RF moves here with a factor 1/2. My image moves here to minus IF. Okay? So that's what happens when I multiply this part of the spectrum by this. Now let's multiply this part of the spectrum. Well, then we see that it's the negative frequency components that create the image problem. So basically the negative frequency components so if somehow we could do something with this negative frequency component and cancel it out, then we would get rid of the image problem. Okay? Yes?
When you're multiplying by the e to the j omega mt, are you actually multiplying by a cosine? Or are you just multiplying by...
I'm assuming that somehow or another I could multiply by this alone.
Okay.
In real life, of course, you can't do that.
Okay.
Okay? All right, so what I'm going to do now is try to show you how this image rejection scheme works based on what we've learned so far. Okay. So first of all, I'm going to put in low-pass filters to get rid of the up conversion. I'm just going to focus on the down conversion. And I'm going to introduce a phase delay here, which, as we'll see, is going to be critical. Let's call the signal at this point A, the signal at this point B, and the signal at this point C. Okay? And let's assume that our input spectrum looks like this. So this is our LO, this is our RF, and this is our image. Okay, so let me plot what happens to our signal at point A. So point A corresponds to multiplying by sine. Okay, so I can do that in two parts. So I know that if I multiply by the first term, which is the positive frequency, I get the following. This is my IF. And there's a factor of j over 2 because sine has an extra j in it, right? So this is the first term. The second term is either the minus, and it also has a minus sign because it's basically it's a sine. So these are the waveforms which are summed together, and I'm keeping them separate at point A. Okay? So this first term corresponds to just shifting this down to IF when I multiply by e to the plus j omega naught t, right? And then there's a factor, extra factor of over 2j in there. And the second term corresponds to this being multiplied by e to the minus j omega naught t. Okay? How about at position B? Well, position B is also very similar. I just don't have those extra factors of negative in there because it's a cosine. So at position B, I also get a shift term with a gain of just 1/2 now. There's no j because it's cosine. And likewise, for the negative frequencies, I get the same thing flipped around. And again, there's no factor of j here. All right? Now we begin to see how we might possibly perform image rejection. Okay? So right now, this is the image term writing on top here that we'd like to get rid of. You can see here the image term is actually out of phase. So if I sum these two signals together, this image term would cancel out, but then so would the signal term, right? You can see if I sum these directly, the signals will cancel out. On the other hand, if I put a phase delay on A, remember, the phase delay affects the negative frequencies differently from the positive frequencies. So it multiplies by plus j in the negative frequencies and minus j the positive frequencies. So that would actually flip things around in a way that would make things favorable. So let me show what happens when I flip things around. So this is going to be at point C. Which is a shifted version of A. Okay? So when I shift this, I multiply by minus j at the positive frequencies. So this just turns into 1/2. And at the negative frequencies, I multiply by just j. So that produced j squared minus 1, so it flips the sign. Okay? And likewise, for this spectrum here, it just comes through without a change of sign. Whereas here, it flips. Okay? Make sure I did that right. Okay, that looks right. Okay? So now what I'm going to do is I'm going to add waveforms B and C. So this is the output. And so now if I add B and C, you can see that here, in these two waveforms, the signals add together, whereas here, they subtract out. Likewise, these two add together, but here they subtract out. So what I end up with is a nice, basically, it's exactly what I want. It's my signal which gets down converted, and my image gets rejected. And you can easily verify that instead of adding these two signals, if I had subtracted it, the image would have made it through and the signal would have gotten rejected. And of course, which one is your image, which one is your RF is kind of arbitrary. It's whatever you like. Remember, that's if I can either inject my LO above or below the signal. Okay? Questions? Yes?
So are you saying that that center frequency is IF?
Yep.
But isn't it that the negative frequencies are rejected? Or the negative frequencies get flipped? So like if it's...
So there'll be a corresponding thing at negative frequency. So here I'm only showing what happens to the positive frequency components. Okay.
Well, in that case, why is the... If it's centered around IF, why is the sign flipped?
Yeah, let me actually do this differently. You're right, I screwed up. Thank you. Thanks for catching that. This should be DC, actually. So this is an example only applies for direct conversion. Okay, at least one person's awake today. Not me. Al?
Would the IF just be the center frequency of your information?
Yeah, but he's right, and when you... Because I applied the Hilbert transform, it wouldn't apply unless the frequencies were negative. I mean, you can do this with... you don't have to go to DC, but this particular example I just did only works for direct conversion. You do. We talked about that last lecture, right? Because what happens is that you're your own image, but you get flipped on top of yourself in the wrong direction. Okay? So this example is for direct conversion. Also works for an IF, basically. Okay? Well, if you go back and look at this architecture, and you do this analysis, basically since we have a cancellation that occurs, it's very sensitive to the gain in each path and the phase in each path. So here, mathematically, it was easy to say that the gain is plus 1/2 or minus 1/2, or phase is exactly 90 degrees or minus 90 degrees. But in reality, of course, if we build these with circuits, there's going to be an issue with matching the phase and magnitude in these two paths. So right away, you can see that this implementation here is already asymmetric because one path has a 90 degree in it and the other one doesn't. Anyone think of a simple way of solving that problem? Yeah, exactly. So all that's important is the relative phase difference between this path and this path, not the absolute phase. So instead of doing 90 degrees, what if I put 2 phase shifts in each path? So for instance, here's a more practical implementation. So this could be plus or minus depending on if it's upper side injection or lower side injection. And in fact, even for the LO itself, I can start out from a single LO, phase shift it by 45 degrees and minus 45 degrees. So this produces in phase and quadrature phase, I and Q. And because each path now is very symmetric, so going from here, I hit the mixer, I hit a phase shifter, I go to the output to a summer. Likewise here, I hit mixer, phase shifter. It's easier to make these two paths match now, phase and amplitude. Likewise here, it's easier to inject the same amplitude and phase shift on the LOs. I want an exact quadrature. If the quadrature is just a little bit off, even if a couple degrees, it destroys the balance in this circuit. So the next question you may ask is, how do you build these phase shifters? And there's a really easy way of building these phase shifters. So 45-degree phase shifters are simply RC circuits. So this is a low-pass filter, and likewise a high-pass filter. Okay, this is RC, this is CR. So if I connect this to the same voltage, and I look at V1 versus V2, so the transfer function H1 is just a voltage divider, 1 over j omega c, R plus 1 over j omega c, which is just 1 plus j omega RC. H2, on the other hand, is just R over R plus 1 over j omega RC, or it's j omega RC, 1 plus j omega RC. Okay? So this is a standard high-pass, low-pass transfer function. Let's see what happens at the frequency 1 over RC. Well, that just gives us 1 plus j, which is 1 over square root of 2 with an angle of minus 45 degrees. And H2 at frequency 1 over RC is just j over 1 plus j, which is also 1 over root 2, 90 minus 45, or plus 45 degrees. Okay. Question, Kevin?
Yeah, so typically are R and C going to be tunable?
You have a good point. As we've drawn it, this only works for a single frequency, so it would only actually work for narrowband signal. If you want to make a broadband version of this, it's basically a polyphase filter. You can do a multi-section version of this, and you get more broadband capability.
I guess my question is, if we're not going to tune it, why not just have a longer piece of trace for one of the signals?
Okay. Well, because to get a 90-degree phase shift would require a really long piece of wire. That's quarter wavelength. So if you think about it, at a gigahertz, the wavelength is on the order of centimeters on chip. So you need a quarter of a centimeter to get 90 degrees phase shift. No, but it's a totally valid question. That's how you do it at really high frequencies. If you go to really high frequencies, you basically use transmission lines to build phase shifters. And actually, transmission lines are superior because it's a real phase shift, right? It's a real phase delay. Okay. Let me just say a few words about matching. So matching is very important, and you're going to explore this in your homework. What you can do is, if you do the algebra, it's a little bit messy, but at the end of the day, you can come up with a curve that looks something like this. On the x-axis, I'm going to draw the amount of gain error. Let's call this the gain error in dB. So 0 dB means there's no gain error. Both paths have the same gain. 0.2 dB means that one path has 0.2 dB more or less gain than the other. On the y-axis, I'm going to plot the phase error, 1 degree, 2 degrees, 3 degrees, 4, 5, up to 6 degrees. So this is the phase error in degrees. And what you can do is you can plot contours of basically constant image rejection. So just roughly, you'll find that if you want 30 dB of image rejection, you have to basically lie somewhere on this contour. So if you have up to 0.6 dB of gain error, you cannot tolerate any phase error. But let's say you have 0.2 dB of gain error, you might be able to tolerate as much as 3 degrees of phase error and still get 30 dB of image rejection. Of course, as you go out more and more, so somewhere out here, this would be a 20 dB image rejection. The more gain error and phase error you have, of course, the less image rejection that you have. And if you want a lot of basically image rejection, you have to be over here, which requires very, very precise components. Now in real life, you'll never get that much precision. So the only way to get to, let's say, more than 40 dB of image rejection is some kind of calibration scheme. You need to actually tune your components to get that much image rejection. Okay, questions?
Don't you have it backwards? I mean, as more error, getting more rejection?
No, no. If you have more and more gain error, right, you get less rejection.
So less rejection, so the output number is going.
So 20 dB means I'm rejecting my image by only 20 dB.
And you have three. Oh, it's not.
So this is the image rejection. So this is a contour of constant image rejection.
Okay, that's 30 dB. I thought it was 3.
Sorry, yeah, these pens are hard to write with. Okay. Any other questions? Okay. I think that's all I'll say for basically kind of a system perspective of mixers. I encourage you guys to read the textbooks. I've put up some links to some sections if you're more interested in this material, and certainly you'll get to explore this as you do your homework. Speaking of which, homework has been posted online, and it's due next Thursday. Okay, so now we're going to transition and talk about basically how we build mixers with real transistors. Before we can do that, we have to talk about the concept of large signal drive. Okay, so by large signal drive, let's take a bipolar as an example. What I mean is that I'm going to bias my bipolar device at some voltage VA, and I'm going to drive it with some signal VI. VI is going to be basically some sinusoid with a significantly large amplitude. Okay? Now before, when we talked about distortion, the assumption was always that, you know, the signal is bigger than a small signal, but not too much bigger, because if it got too much bigger, we'd have to keep more than cubic terms around in our power series expansion. Now what we're going to do is we're going to say Vin is a large signal. It's no longer restricted to be a small signal. Okay? And let's see if we can analyze what the collector current does as we make this signal larger and larger. Okay? Let me make sure that the distinction between large signal and small signal is clear. Any questions about that? Good. I think it'll become more clear as we go through this example. Well, let's assume that no matter how large Vin is, the device does not leave a forward active region, so that this equation is always valid. Okay? And VBE in this case is some bias voltage plus this input signal. So this is the large signal sinusoid drive. Okay. Now it turns out that this kind of analysis is very useful in many circuits, in mixers, as we'll see in this lecture, but also frequency multipliers and basically class C amplifiers. So this is not just strictly for mixers, it's actually a pretty nice general concept. Okay? Well, let's look at this equation. This is the bias term. And then we have a term which is the input signal normalized to Vt, which is Kt over Q, times cosine omega t. And we can write this in normalized form, e to the a, e to the b, cosine omega t, where a is basically the bias voltage, VA divided by Vt, and b is the normalized input signal. Okay, and the important observation, if I look at this signal, it's a periodic signal, and so I can do Fourier analysis on it. Okay, and if you do that, or if you're like me, you just go into Mathematica and you punch in this number and you say, this function, and you say, what's the Fourier series for it? What you discover is that actually it's one of those nice tabulated functions. It's a modified Bessel function. So here the i's are modified Bessel functions of order k. Now, make sure you distinguish between i's and j's, right? You're probably familiar with Bessel functions. Anytime you have a problem with cylindrical symmetry, you get a Bessel function, which is a periodic function in cylindrical coordinates. These functions are more like exponentials. So it's like the analogy between hyperbolic functions and sinusoidal functions. The j's are kind of like the sinusoidal functions, and the i's are more like the hyperbolic functions. Okay. Okay. So no magic here. All I've done is said, what's the Fourier series for this? So the Fourier series has a DC term at cosine omega t, cosine at 2 omega t, and so on. Because of the even symmetry here, it's a cosine series. There's no sine terms. And the coefficients are just these modified Bessel functions. Okay? Yes, in the back.
Question regarding the analysis tool in here. In last lecture, talking about nonlinear analysis. Again, in the context of large signal, we used polynomial series or Taylor series. What's the benefit of using this new tool to analyze large signal?
Yeah, that's a good question. I was hoping somebody would ask. So if we go back here and look, if I wanted to use a power series expansion, I would just take this exponential and do a power series on it, right? That's what we did earlier in the lecture. But the signal would have to be relatively small relative to Vt for the power series expansion to be valid, right? Otherwise, I'd have to carry 100 terms. So VBE would have to be the signal component, V input, should be smaller than Vt, roughly, to make this power series valid. Now I want to make V input arbitrary. I want to make it a volt, let's say. And I don't want to do power series with 100 terms. So instead, I just say, I get what I get. At the end of the day, I'm just going to take its Fourier transform and look at what frequency components come. Because it's periodic, I get a Fourier series. Okay? Okay? So given that we know that the bias current, that this e to the b cosine omega t gives us this series, we can now write the collector current in general as e to the a I0b. I'm just going to factor out this constant term, plus 1 plus 2I1b I0b cosine omega t plus 2I2b I0b cosine 2 omega t, and so on. And this I will just call IQ. Right? The reason I factor out this term here is that very often when we design circuits, we actually have the means of holding the bias current constant. It might be like biasing through a current mirror or using emitter degeneration. But there is some means of holding the bias current roughly constant. So as I apply my large signal, this is what happens in general. I0 as a function of B actually will increase. We already know that. We know that all second order nonlinear terms generate DC. So the DC level of the circuit would shift. But in reality, I'm actually going to have some external circuitry to keep IQ constant. So what I'm going to do here is assume IQ held constant. Okay. So here I have a plot we can look at. Can we zoom into this plot? Thank you. So all I've plotted here is that collector current waveform, and it has basically what I should have written down what B is in this example. I didn't. But what's interesting is you see that the collector current waveform, even though the input is sinusoidal, the collector current waveform has this very peaky response. When it's positive, the current shoots up, right? This is IC divided by IQ. So you can see that the collector current is 5 times larger than its bias, which is at 1. And then when the VBE goes negative, the current essentially goes to 0. The device shuts off. So as a function of B, I can plot this a little more carefully. Yes?
What's the x-axis plot?
Is
Oh.
that time?
This is time, yeah. Sorry. So this is basically normalized time. So it's normalized period. So what you can see here is that B is equal to 0.5. The collector current looks almost sinusoidal, right? So that's about 12 millivolts of voltage. As I make B larger and larger, so here B is equal to 4, the collector current becomes more and more peaky. This is B is equal to 10. You can see now the current is really shooting up. Okay? So again, to answer the question that was raised earlier, this analysis lets us understand the collector current for an arbitrary value of input waveform. Okay? In fact, I can go ahead and make a plot like this. Again, in any program, most programs know these functions. They're very well-known tabulated functions. So here I'm plotting In divided by I0 for a case where I'm holding the DC current constant. So this is a magnitude of the first harmonic of the current, right? This is a magnitude of the second harmonic. So this is a second order distortion. This is the third, fourth, and so on. And so basically for any given value, so the x-axis here is B as a function of the input drive, and the y-axis is the magnitude of the nth harmonic. So if I have this table, I can just look up for any value of input drive what the various harmonics are going to be. So for a value of B is equal to 10, you can see that the first harmonic is actually approaching 2, because remember the actual harmonic is 2 times this. For a very, very strong overdrive, the first harmonic is actually twice as big as the bias current. And then the second harmonic and third harmonic and so on and so forth. Okay. So the interesting takeaway point is that if you zoom into this curve, this is the small signal regime that we studied with power series. In fact, I've done that here for you. So this is zooming in, and you can see that this is a nice linear line. It's telling me that as I increase the input power, the output power is increasing in step. And this is how much the second order is increasing, right? For very small signals, this should increase roughly like x squared, right, or b squared. And so at very small values, I would expect this to be parabolic. And this should be like x cubed or b cubed, and so on and so forth. But as I go out, where b becomes substantially large, the deviation, it's the fourth order or sixth order terms come into play and make this curve more complicated. Okay? Any questions? Yes.
What's a Bessel function?
You can look it up after class. For now, just imagine it's just some function, right? I'm just telling you that you do. Sometimes in life you get lucky, right? So somebody did this analysis and did the Fourier series and said, ah, this is a Bessel function. And now to you, you say, well, who cares, right? But you know, back in the old days, people solved a lot more differential equations than we do nowadays. Now we have computers, so we're lazy. But back in the old days, people solved differential equations by hand, and so Bessel function is as familiar to them as sine and cosine, or is as well, maybe not as, but pretty familiar, right? So it's one of those functions that you know and you love. Okay. Another one question?
Well, actually, just, I mean, I've heard about it in every other class, but no one has ever been talked about it. Like, I guess you already answered that.
Yeah. There's basically, the reason it's called the Bessel function is because one of the Bessel brothers initially found a differential equation whose solution was the Bessel function. And back in those days, the way you solved differential equations, actually a very common way, was a power series solution. So you'd assume that the solution was a power series. You plug the power series into the differential equation, and then you'd find a formula for the coefficients of the power series. And then once you'd done that, you could call the function after yourself. Hence the Bessel function. Okay? So actually a very simple example would be take this function, y prime plus y is equal to 0. Pretend like you didn't know what the solution is, right? Assume the solution is an basically y to the n 0 to infinity. Plug in here, take its derivative, plug it in, and solve for an. And what you discover, right, is an, so this would be cosine, right, or sine. So you'd find that there's two possible solutions, and the solutions have coefficients that go -1 to the 2n plus 1 to n plus 1 factorial, right? And that's your sine and cosine. Okay, let's get back to circuits. So let's look at how we actually create this stable bias. So if you actually bias in a non-IC environment, back in the old days, this is how you biased up a bipolar device. So this is VA. And as you guys know, you can't just put the emitter to ground. You would get a very, very bad biasing circuit. That's because the collector current is very sensitive to VA, and any temperature variation or process variation would change the current. On the other hand, if I use a resistor on the emitter, that stabilizes the bias. So let me calculate the value of VA prime here. I don't know why I called it prime, but let's see why. This would give, neglecting base current, this is R2 over R1 plus R2 times VCC. Okay? And VE is VA prime minus VBE. And so then the collector current, IQ, is VE over RE, which is VA prime minus VBE divided by RE. Now the idea is that this is a good biasing scheme because VBE is more or less very insensitive to the actual current value, right? It's a logarithmic function of the current value. And VA, because base current is very small, is more or less just fixed at some fraction of VCC. And so this will give me a nice collector current, which is independent of temperature and bias. But of course, this would reduce my gain, so I use a bypass capacitor here. So this is an emitter bypass capacitor. Okay. Now the reason why this circuit actually has, why I claim that this has a stable bias, is that imagine now that I bring in a large signal here. This large signal will generate even order distortion through this nonlinearity, which would tend to increase the DC current, right? As the DC current increased, that would actually increase the average voltage here, which would reduce VBE, which would actually tend to decrease the DC current. So intuitively, we can see that the action of RE is negative feedback for the bias current, which forces the current to average out to this value. Okay. Now this is the old days using discrete transistors. Nowadays, the way we would bias this up would be through a current mirror, right? So let's say this is a current mirror. This is our device. I might use a resistor to isolate this device and use a capacitor here to compensate this feedback loop and bring in my signal here. And you can see that as I increase the magnitude of this signal, the average voltage here has to equal to the average voltage here, and that would tend to stabilize the bias. Okay. Now there's other kinds of, so this is an IC biasing scheme. Yes.
Could you just explain the function of that resistance and capacitance once again?
Sure. So this resistance is there because I don't want my input signal to modulate this. I want this to be constant. So this resistor tends to reject that. So it introduces a large, this might be 100K. So that signal that reaches here gets attenuated by the input impedance divided by 100K. Now the input impedance of shunt feedback is very low, right? It's roughly 1 over GM divided by beta. So this could be a few ohms. So the rejection is a few ohms over 100K. Almost nothing. This capacitor is here because this is a feedback loop and I need to compensate it. Okay? So this is a compensation capacitor. And this is basically a filter. Okay. I could have also just used a simple mirror. And the circuit would also work fine. The difference now is that, first of all, I have base current. And if base current flows through this resistor, it varies the VBE of this device, right? So that's kind of bad. I'd like to get rid of that because base current varies over temperature a lot due to beta variations. So here, this is basically a helper transistor to lower the base current. And in CMOS technology, that's not an issue. But the other nice thing about this shunt feedback is it lowers the input impedance. Here, the input impedance is about 1 over GM, right? Here, it's much lower. Okay. Well, the same approach that we use for the single device can also be applied to a differential pair. Okay. Unfortunately, for a differential pair, there is no closed form solution like there was for the Bessel functions. Okay. So if I actually do this with well, let me just try to draw it. So here is the idea. I have a differential pair with current IEE, and I apply a voltage B cosine omega t times Vt across here. Okay. Now, right away, I know if I apply an extremely large signal, right, much, much bigger than kT over Q, that will produce complete shifting of the current. So if I were to look at just the current through here, let's say IC1, well, let me write down the equations. I know that the sum of these currents, well, let me just finish that thought. Without doing any analysis, I know that if I apply a very large signal, when the signal is very negative, all this current IEE flows through Q1. When the voltage is positive, all of it would flow through Q2. So if I were to draw, let's say IC1 over IEE as a function of time, it would basically break down into a square wave. So this is when it's negative, this is when it's positive. And as you could imagine, as you lower the input voltage, if you make it very small, then the average current through here is basically IEE over 2, and it would be a sinusoidal kind of signal. And as you increase the amplitude more and more, actually, sorry, this is a bad drawing. Looks like this. As I increase the amplitude more and more, it would tend to approach the square wave in the limit. Okay? So the limiting value for very large B would be basically just a square wave with average value of 1/2, right? And basically fundamental component, which is 2 over pi. And then we all know how a square wave goes. Basically, we get all the odd functions. So 1/5 cosine 5 omega t dot dot dot. Okay? Now, even though this is the limiting value, it turns out that if you put a few hundred millivolts across this differential pair, you get pretty close to this squarish waveform. And this is very convenient for doing simplified analysis, hand analysis. Okay? If you want to be more accurate about it, you could just write down a few equations. You would say, okay, I know that the sum of the collector currents have to equal IEE for a diff pair. Okay? And the difference between the VBEs, which is the input signal, has to be a log of IC1 over IC2. And so therefore, if I solve for IC1, it looks like this. And if the input signal is sinusoid, then IC1 is a periodic waveform which looks like this. And so I could now plot this as a function of B, which I just did, and then I can take its Fourier series and plot the coefficients as a function of B. So let me do that. Let's zoom into this plot here. So this is the differential pair harmonic currents, and this is the fundamental component. You can see that for very large values of B, it approaches 2 over pi asymptotically. And because this is a differential, there's no even terms, only odd terms, right? So this is the third component. You can see the third component initially increases and then saturates at a value of 1/3, right? Minus 1/3. And this should saturate at a value of 1/5. And this should saturate at a value of 1/7, and so on and so forth. Okay, any questions? Now here we can see that the bias current naturally limits, right? That's because, so this waveform here naturally limits. And the reason is there's only current IEE. IC1 can never get bigger than IEE, right? So there's a natural limiting mechanism. And the bipolar amplifier, the limiting mechanism is due to the fact that we somehow force the bias current to be constant. If we don't force the bias currents to be constant, then you'd find that the current just increases without bound. Okay? Okay. So let's now apply this analysis to a mixer. Okay, so the mixer has 3 ports, has an LO, an RF, and an IF port. And we're going to assume that the LO port is pumped with a large signal. And we're also going to assume that the RF port is basically a small signal at some frequency omega s. And let's call this pumping signal omega naught. So if the RF signal is relatively weak, the response of the circuit should be linear, right? But because it's being varied in a time-varying fashion, we would expect the response to be linear time-varying. So let me just write that down. circuit response should be linear, or at best weakly nonlinear. So the Taylor series stuff we did should be valid. But the LO changes the operating point in a periodic fashion. Okay? So we can model this as a small signal output current that is a linear function of the input voltage, a linear transconductance, but a linear time-varying transconductance. So this is LTV, or really linear time-varying periodic. And because G of t is periodic, we can write that, the transconductance, as a Fourier series. And so on. Okay? And now when we apply our input signal, the output signal is this thing, G0, G1 cosine omega naught t plus G2 cosine 2 omega naught t, and so on, times the input, let's say V1 cosine omega st. So we see that the action of a linear time-varying periodic circuit is to take our input signal and multiply it by some DC term, and then to multiply it by cosine, and then multiply it by cosine 2 omega, and cosine 3 omega, and so on and so forth. So the output is G0 V1 cosine omega st. That's just the linear output. And then G1 over 2 cosine times V input, let me call this V input, times cosine omega naught plus or minus omega st. So that's basically frequency modulation by the cosine term. That's kind of the ideal mixer multiplier that we talked about last time. And then G2, the input, gives us cosine 2 omega naught plus or minus omega st, and so on and so forth. So we can see that a linear time-varying periodic circuit is kind of a mixer that generates lots of products. And in theory, we could maybe just filter the circuit and pick off the desired product and ignore all the other products that are generated. Okay? So what we're going to do is we're going to define a conversion gain. Is the transconductance for the desired signal, so the IF output current magnitude divided by the RF input signal voltage. And we can see now that it's just G1 over 2. Okay, any questions? Yes?
So how the assumption that the system is linear is applied in this expression here?
Okay, so let's go back and look at how we set up the problem. This is important. So the assumption we make is our mixer is a 3-port device. It has 3 ports. IF is the output port, RF is the input port, and LO is where we apply our local oscillator. We assume the LO is very strong, right? So it's a very strong signal, so it will actually periodically alter the operating point of our circuit. The RF, though, we assume is very small, very weak. So the RF port should essentially see a linear circuit. But it's a linear time-varying circuit because of the action of the LO port. So as far as the circuit's concerned, from the RF port's perspective, it's a small signal circuit. But from the LO's port's perspective, it's a large signal circuit.
Earlier, where the expression you have, I can see time-variant essence in here, but I think the same equation would apply to the nonlinear system.
No. Okay, so if we wanted to include nonlinearity, then we would include basically the fact that the input voltage should not see a linear function, but it should see a Taylor series expansion. but the Taylor series coefficients would be a function of time. We'll do that in next lecture, actually. So be patient. Let's take things one step at a time. All right. Make sense?
I have a question.
Yes.
So, if the local oscillator signal is a perfect sinusoid, and is this means these harmonics 2 omega naught, these are generated because of the nonlinearity of the circuit?
Yeah. Even if you have we assumed that the LO is a perfect sinusoid, right? We could assume that. We did that when we looked at the large signal behavior of a differential pair or a single transistor, and even there we get harmonics. But actually, for this analysis that we just did to be valid, all we have to assume is the LO is some periodic function. Doesn't necessarily have to be sinusoid. Okay, that's a good question.
Just could you go back to the other slide, the final slide with the conversion gain? Oh, just so I could look at it. That's G1 over 2?
Yep. G1 is the first harmonic of the periodic. So G conversion, it looks like there's a transconductance between the input and the output. The difference, though, is that the input and output are at different frequencies. That's why we call it a conversion gain. So signal comes in at frequency omega s. The output current is at frequency omega s minus omega naught. So the input is small at frequency omega s. It goes into the mixer. The mixer is getting pumped by this large LO signal. And the output could be larger, there could be gain, is at some IF frequency. Okay? And if this is magnitude V input, this current magnitude is G1 over 2 times V input. And there could be harmonics in here. But for now, let's say we filter out those harmonics. Okay? Yes?
One question. So why the mixer has to be pumped with large signal oscillators? What if it's much
That's
bigger?
actually a very good question. If you think so why large signal LO? Well, actually, I can have any nonlinearity. Any arbitrary nonlinearity, right? And if I just sum my LO plus my RF, somehow or another, right? Maybe I use a transformer. So I have my LO, I have my RF, and I take the sum, or I might do current domain summing, right? And then I apply it to some nonlinear function. Then I know that the output will contain omega LO plus omega RF, omega LO minus omega RF, right? And it will also contain 2 omega LO plus omega RF and every other product. So the output will have K omega LO plus J omega RF for all Kj, right? That's a mixer, right? I just pick off this term. I have a filter at the output. And so this is another way of building a mixer. So what is the advantage of making the LO signal large? Well, the advantage is the conversion gain of this mixer is quite low. In fact, I'll encourage you guys to analyze this, maybe in a homework, or maybe on a midterm or final, and compare the conversion gain of this circuit to the one we just analyzed. But it's a very good question. It's a very valid point. Essentially, any nonlinear circuit, if you put in your LO and RF, it will generate conversion products. Okay, so in the last few minutes, I want to show you guys a BJT mixer with a single transistor, and next lecture we'll analyze it in more detail. So here I have basically a transistor. I'm going to bias it up just as we showed before. At this port, I'll apply my LO. And then at this port, I'll apply my RF. And this is just DC here. And this is a bypass capacitor, and this is L3C3. Okay? So next lecture we'll analyze this in detail, but right now let's see how the circuit could work. This network just biases up my transistor, and I apply that bias voltage through this transformer, and that establishes EVP. Of course, I use an emitter resistor here to stabilize the bias point. Then I apply a large LO signal, which will basically generate a time-varying transconductance in this device. And then I apply a small RF signal, which gets converted into the output current at the IF frequency, and so I have a filter here to pick off my IF frequency. So this is tuned to IF, this is tuned to RF, and this is tuned to LO. Okay. We'll analyze this in detail in next lecture. Questions?